Okay, so we're looking at the problem that says, which of the following could be produced if chloric acid dissociated in water? All right, so there's four options there. So let's just look at chloric acid dissociating in water real quick. All right, I know that chloric acid is going to start with H. I know that ic used to be 8, so it's going to be ClO3. All right, so there's my chloric acid. All right. Now, if it just dissociated, all right, if it dissociated whether it was in water or not, we know that it's going to be a strong acid, all right, because we've got 3 oxygens and only 1 hydrogen. So my ratio there is going to say, all right, well, it's going to be a strong acid. So it would just simply break apart into these items. So this is in its simplest form, all right, and these 2 items are options on the question. So you'd want to select him and you'd want to select him as possible things that can be created when chloric acid dissociates. Now, most of the time, whenever something is going to dissociate and go into solution, we're using water. So a lot of these dissociation equations have assumed water anyway. However, since we are dealing with an acid, and here's where this question gets tricky, if you write it specifically with water instead of just as a normal dissociation, it becomes a different type of problem. We did one of these in lab where we call this Bronsted-Lowry, all right, which is going to be a relationship between an acid and a base where one is a proton acceptor and one is a proton donor. Now, our notes tell us that acids like to donate protons, while bases like to accept protons. All right? Can you see that? Boom. If we take a look at the relationship here, we know that this is our acid, right? I mean, he's called chloric acid. And water is what's called amphoteric, all right? I haven't taught that word yet. We will. But amphoteric simply refers to a compound that can act both acidic or basic, depending on the scenario. So since we're in this relationship where this is definitely going to act as the acid, then water in this case is going to behave as a base. All right, so if we follow our Bronsted-Lowry rules under this idea, the acid wants to donate a proton to the base, all right, following my Bronsted-Lowry rules. Therefore, as I go over here, I need to write my acid with 1 less H, which is going to create, hey, guess what? This guy here, same thing, right? However, instead of my free-floating H ions, look what happens here. The H plus is accepted by the base. So my water is actually going to accept this extra hydrogen, so let's give it to him. Instead of H2O, now he would be H3O. But not only did he gain an H, he gained a plus. This dude here is known as hydronium. We covered him last year. And in December, we're going to talk a lot more about this Bronsted-Lowry, so I don't want it to freak anybody out that this is a more confusing problem. But now I have a third option that can be selected as a possible product. So 1, 2, 3. Now, there's actually a fourth option, though, and it says electrolytic solution, which is absolutely correct also, because the whole thing for electrolytic solutions is there dissociation happening completely to where there's free-floating ions? And no matter which of these reactions we look at, the spontaneous dissociation or the dissociation specifically in water, all of them produce electrolytic solutions. Did that make sense?